Okay, so much for simple. Unfortunately, we have to do serious. Serious is the S that nobody really wants to talk about, you know? I mean, we got to talk about it because it is serious. It's a very serious problem. But sometimes you could think the middle S might be called scary. It's no fun talking about this middle S, but we got to discuss it. A lot of the problem that I see with climate change communication is people will only talk about the middle S. Okay? They forget about the first S. They sort of show you a graph and figure that you understood it. And then they go right to the second S, and then they beat you over the head and shoulders about how scary and bad it is, and then they wait for you to applaud. And it's just awful. It sucks the soul out of you. It's depressing. You wind up leaving people to go home and cry, or to say that there must be no problem, or to say that it's too late and there's nothing we can do about it anyway. All of these are bad responses, right? So we're going to get to the third S. I promise you, we're not going to stick with this middle S. We always have to talk about it because it's important, but we're going to get past it. So hang in there. This is how much global warming has happened already in the world. It's about 2 degrees Fahrenheit, about 1 degree Celsius, average global warming. The different colors are different amount of global warming. You can see that the land warms up a little bit more than the ocean because the oceans are deep. But there's about 1 degree Celsius of global warming in the world since the year 1900. Here's the choice that we have to make. That's that same map on top. That's global warming up to now. And here's one version of global warming for the rest of the century, and there's another version of global warming for the rest of the century. And the colors are the same in all the maps. And you can see that we have one possible future that looks actually quite a bit warmer than today up in the Arctic, but for much of the world is not that much warmer than it is today. Or we have this, purple hellscape over on the right, which is what we really don't want to go there. And the difference between this bottom left map and that purple map over there is all about future decisions that people make. How much coal, oil, and gas they wind up burning. So kind of one of the big problems here in the world is that, here's the graph of all that warming up to now in the black. And then the blue curve into the future shows what if we decide to kind of keep warming to a reasonable level versus the red curve, which is like, woohoo, burn it all, let's just go for it. And the trouble is that we have to make this decision now, but if you look like for the next 20 years or so, these colors are not that different. So you're making a decision now to follow that blue curve instead of the red curve, but it doesn't really pay off until later. So, I don't know, students in here are like 20, right? 21-ish. I don't know, by 2050, you're going to be a lot older, but it's really your children out here around 2100 that see the big difference between this red line and the blue line, and that's the difference that depends on the choices that we have to make right now in our world. Here's 3 different versions of the world. There's a low emissions world, a medium emissions world, and a high emissions world. And each of the different maps shows how much warming by the end of the century. And you notice that they're not all the same color. So, for example, you notice that there's way more warming on the land than there is in the ocean. I mentioned that a minute ago. It's because the oceans are deep. On the average, the oceans are 13,000 feet deep. Can you imagine that, 13,000 feet of water? Remember my 4-watt light bulb? That extra CO2 gives you a 4-watt light bulb on every square meter. 4 watts of heat on 13,000 feet of ocean doesn't warm the ocean all that much. It's a lot of water. Versus that same 4 watts on land warms it up more. So you get more on land. If you notice in the southern hemisphere, you get less than you get in the northern hemisphere, and that's because the southern hemisphere is mostly water, the northern hemisphere is mostly land. A third thing you might notice is that way up in the Arctic there where the snow and ice is, it warms up way more than any place else, and that's because snow and ice is bright and white, reflects the sun to space, and if you warm it up enough to melt the snow and ice, then you get extra. You don't just get the heat down from the CO2 molecules, you also get all the extra sunshine that you soak up, that you absorb when the snow and ice goes away. So if you happen to live on land in the northern hemisphere where it snows, you get extra. you don't just get global warming, you get about global warming and a half. And guess what? That's where we live, right? In the middle of North America, in that low emissions world, that's about 3 degrees of warming. And in the high emissions world, that's about 6 degrees of warming. Oh, but wait, those are Celsius degrees, because science. So, you know, if you want to convert to the kind of degrees that we use in day-to-day life, Fahrenheit degrees, you got to multiply almost by 2 again. So it's like you get a half again because of where you live, and then you get like another factor of 1.8 because you use Fahrenheit in your lives instead of Celsius. So instead of 3 to 6 degrees, now it's 5 to 10 degrees Fahrenheit around here. And even that doesn't sound too bad. I don't know, it was like 55 out today. So, you know, an extra 10 degrees would have been 65. That's not the end of the world. But we're not just talking about today. We're not talking about like on one afternoon, 10 degrees of warming. We're talking about on the average. And nobody has a clue what average 10 degrees of warming looks like unless you look at a map. So here's a map of temperature, high temperatures in the United States in Fahrenheit, which are the degrees you're used to. And each color on the map is 5 degrees. I got one for Denver. I got one for Seattle. I got one for Washington, D.C. I tried to put one here for Whitewater. I'm not sure that's exactly where Whitewater is, but it's close. So what I'm going to do now is each color on the map is 5 degrees. So 10 degrees of warming means you move 2 colors on the map. So let's move our dots. And it turns out that, oh, actually, 10 degrees of warming is a lot. 10 degrees of warming means you're moving to Memphis. 10 degrees of warming means I'm moving to Albuquerque, and like the people in Washington, D.C. are moving to Tallahassee. Well, maybe that'd be good for them. I don't know. But 10 degrees of warming is a boatload of warming. If you were a farmer and you swapped out the climate of Tennessee for the climate of Wisconsin, you would notice. You would totally notice. It's like moving 600 or 800 miles south. It's a huge thing. And it's not like slowly, like at the end of the Ice Ages, over thousands of years, these things happen. We're talking about like by the time your children are your age. Holy mackerel, that's a lot of warming. Warm air evaporates more water. Now, everybody pretty much knows this, right? If you don't believe me, try it on the stove at home. Put a pot of cold water and a pot of hot water and see which one evaporates faster. But I mean, everybody knows this. Where I live, we would not have green lawns if we didn't have sprinklers. And boy, howdy, you have to use more water out of your sprinklers on a hot summer day than you do on a cool day. And in agriculture, we have evaporative demand of our crops. They need more water when it's hot. And if you swap out the climate of Tennessee for the climate of Wisconsin, you're going to need more water. You know, it's got to come from someplace. Sure, if it rains a lot more, great. But I'll guarantee you it's going to evaporate a lot more, and you're going to want more than you use today. So drought is not just a lack of rainfall. Drought is a running sum of water in minus water out. And if you increase the water out, just like heat in minus heat out, right? Water in minus water out. If you increase the water out, you get more drought. So there's more drought in a hotter world. There just is. Doesn't mean it's not going to rain. It means you need more water. These are some estimates from American Climate Perspectives of changes in crop yields in this part of the United States. I don't know, can you recognize that? Wisconsin's like there, right? There. And this is kind of now and later and later. Parts of southern Wisconsin on the order of 25 to 50% reduced crop yields, and almost entirely due to the heat and the lack of water, the extra drought that occurs when it's hot. This is a pretty significant change. If you went way up north, like Bemidji, Minnesota, probably good for crops there, right? But Illinois, Iowa, Missouri, not so good. You guys are sort of at the edge where it starts to turn from good to bad. Now, you guys aren't anywhere near the coasts, and that's a good thing. But I want to talk to you just a little bit about how this works on coasts, because there's a kind of like misconception that we had with the reasons for climate change. There's a misconception about how sea level rise is this gradual thing. You know, you've all seen these animations, right, on websites that show the blue stain that sort of creeps up over things. And that's bad. Sure, if your city's underwater, that's bad. But I'm going to tell you that it's actually impacts places long before they're underwater. has to do with coastal flooding. So coastal floods are kind of weird. There's this big wind that comes and it pushes the water up onto the land. It's called storm surge. And you know, we saw lots of evidence of this past summer in the hurricanes that came through. So obviously big storms happen less often than small storms. Good thing, right? So this bottom axis here is how often or how many years in between floods of a particular height. And this happens to be data for New York City. So, you know, a 100-year storm might be, whatever that is, 7 feet of water, and a 1,000-year storm might be, you know, 10 feet of water, and so forth. So the big storms happen much less often. That's a good thing. So what I'm going to do is I'm going to do that same exact data, only now just sort of as a sketch. So it's pretty much the same as I just showed you, a 100-year flood of like 8 feet, 1,000-year flood of whatever that is, 12 feet. The trouble with sea level isn't that the water comes into your neighborhood permanently, it's that you lift this line. So if you have 3 feet of sea level, think of it as just the whole line moves up by 3 feet. So what was a 100-year flood, you know, over here at like 8 feet, we're going to slide that line, slide that line up, there it goes, like I said. And that same flood that used to be a once-in-a-100-year event winds up becoming like a once-in-a-10-year event. Now that was the flood in Hurricane Sandy that flooded the subway, was this sort of 100-year flood. And if it happens once in 100 years, you just rebuild it. And it sucks, and it costs billions of dollars, and you know it's a big inconvenience, but you can rebuild it. It's a different story if it happens every 10 years, though. If it happens every 10 years, you wind up moving. This is Hurricane Sandy coming in the subways in New York City. I mean, this is the ocean coming down the stairs and flooding into the subway tunnels and you know, basically shorting out all those electrical things down in the subways. I got some other kind of bad news for you, which is that this really isn't mostly about us. And by us, I mean the us that has lots of money and uses lots of energy. These are 2 photographs taken from the same spot. See this clock tower in the front? I walked past that clock tower. It's in Shanghai. And it's just, you know, looks on this side of the river like you know, German colonial architecture or something. I think it is. And on the other side of the river, in 1991, there was basically nothing over there. And by 2012, holy mackerel, it's the capital of the world on the other side of that river. Shanghai's got more people living inside the city limits than any other city in the world. 22 million people in the city of Shanghai, 3 times as many as New York City. Shanghai's surrounded by suburbs that you've never heard of, and every one of those suburbs has more than 10 million people in it. Shanghai metro area is about 75 million people. And what you're seeing in these 2 pictures that are taken 20 years apart is not population growth, it's economic growth. It's a good thing. It's because billions of people live in dire poverty, but not anymore, or not so much anymore. It turns out there's about 7 billion people on Earth, but there's only about 1 billion people like us. By people like us, I mean people who use a lot of energy. And the world's population is increasing. We expect about 30% increase in the population of the world in this century, but we expect that this 1 billion energy users will turn into 4 billion energy users. So this is 10 times the rate of population growth. You think population is growing fast? Energy use is growing 10 times the rate of population. If population grows 300%, if energy use grows 300% in this century, and that 300% is done with coal, oil, and gas, we are in a world of hurt. I'm telling you, there are a lot of people in the world that need to use more energy than they use today. And that accommodating that development is going to be very, very difficult if we use carbon-based fuels to do it. I got one other bad piece of news for you, which is that it's a very long-term process. So, sorry, I said I wasn't going to use so many graphs, but these are some graphs. These are some graphs that start in the year 1800, like back when Thomas Jefferson was president, and they go out to the year 2300, which is like between the Star Trek and the Next Generation or something like that. It's like ridiculously far out in the future, okay? So 500 years. This bottom graph is CO2 emissions in billions of tons of carbon per year up to today. You are here. We burn about 10 billion tons of carbon a year. And then I have a what if that follows sort of development of China and India and then Africa with fossil fuels up to about 30 gigatons per year of CO2 emissions by the end of the century. And then on January 1st of 2001, I just said, woohoo, Happy New Year, we're turning them off. And it goes all the way back down to zero. Look what happens to CO2 if that happens. Here's a CO2 back in 1800. Here's a CO2 today. It's just not that different from what it was in 1800. But if we follow this red curve, that CO2 goes way up. Not twice as much as it was back in the day, but 4 times as much as it was back in the day. And then when we turn off the tap, look what happens to CO2. Almost nothing happens to the CO2. And that's because CO2 is not a reactive gas. It's not like the brown cloud, the smog, where if on Saturday you don't drive, the CO2 just like burns off. It doesn't do that. It's not a reactive gas. It just accumulates in the atmosphere. And it takes thousands of years for that to go away. If China and India industrialize with coal, the CO2 will rise to 4 times pre-industrial. So that's not one 4-out light bulb on every 2 seats. That's one 4-out light bulb on every seat in this whole auditorium and the entire world, and we leave them on for thousands of years. That's a really bad idea. The thermostat basically has a ratchet in it. You can turn it up, but you can't turn it back down. So this is like bad myth number 2, which is that once we figure this out and we stop setting coal on fire, the problem will go away. Stuff will go back to normal. This is not a problem that goes away. This is a problem you can make it worse and worse and worse and worse until you stop making it worse, and then it doesn't get better. This is kind of a weird graph. This is sea level versus temperature. Now, I've noticed walking around campus today, there's a Laurentide Hall, and there's an Esker, and there was another thing Holly told me about. The what? The drumlin, yes, the drumlin and the Esker. So you guys know about ice ages. Arr. So 20,000 years ago, it was cold, right? It was a few degrees colder, maybe about 5 degrees colder, 6 degrees colder Celsius than it is today in the world. And the seas were way lower. This is in meters, so 100 meters, 300 feet lower seas. Why? Because when it was freezing ass cold, all of that water came out of the ocean to build all those giant ice sheets on North America and Europe and Asia. So that's because the ice on land took away water from the oceans. Then it melted and it went up to where we are today. 3 million years ago, it was only about 1 degree warmer than it is today, but the ocean was 20, 30 meters higher. 20 meters, like 60 feet, that's a lot. Higher than it is today. 40 million years ago, it was warmer and the oceans were much higher, 200 feet higher than they are today. And according to our climate models, 100 years from now, it's going to be warmer, about 3 degrees warmer than today, but the sea level is only going to be about 1 meter higher. 1 meter higher is about like that, right? So what's up with this? How come the black line goes on a 45 degree, but that red dot doesn't fall on the black line? The reason why we're not going to get hundreds of feet of sea level rise in this century is because it takes a freaking long time to melt all that ice, right? The melting is slow. We're talking about warming up the climate. This is like plan A, right? Warming up the climate as much in the next 100 years as it warmed up coming out of the last ice age. That's amazing. You know how long it took to warm up coming out of the last ice age? 10,000 years, 100 centuries. And we're going to do it in 1 century. 100 centuries worth of warming in 1 century. If you warmed it up and let the sea level rise to where it was in equilibrium with the temperature, it would rise hundreds of feet again. And the water would rise quite fast. This is what happened when the ice melted the last time. This is thousands of years ago. the ocean was way down, and then about 14,000 years ago, something terrible happened. And the ice started to melt fast, and we call this meltwater pulse 1A. The oceans rose a foot a decade for 400 years. You sort of like picture what that does to New York City or, you know, Shanghai or London or Miami. A foot a decade for 400 years. This is what happens to the United States if the ice all melts. And it ain't going to melt by the end of this century, but that's a very different coastline. Can you see Miami here? It's like 500 miles offshore. The whole East Coast is gone. The Gulf of Mexico is up in Arkansas. I mean, this is like not a small change. We're looking at like massive changes of geography eventually. It takes a long time for that to happen. So we don't want that to happen. I mean, the consequences of letting all that happen are flat out unacceptable. Those are really pretty bad consequences. But it's not the end of the world. It is solvable, and you're going to solve it.